Action Potential by Tyra Bongiorno.
The first drawing I made is of an axon, currently at resting potential that has a level of negative 70 millivolts. On the outside, or extracellular side of the membrane, there are many sodium ions giving the outside of the cell a positive charge. On the inside of the cell, also called intracellular, there are many potassium ions giving the inside a slightly more negative charge. Must be passed down the cell body and through the axon. An action potential is an example of positive feedback in the body because the amplified signal is continuously increased in order to produce output. This car is going to represent a signal traveling down the axon of the cell. Every time there is an impulse, the impulse must reach or exceed a certain intensity level for the reaction to even begin. This is called a threshold. Changes that affect an entire excitable cell membrane to conduct the signal. An excitable cell is a cell that is capable of sending signals. The action potential can be described in a few major steps. Keep in mind that the positively charged ion has more protons and a negatively charged ion has more electrons. To explain the steps, I want to explain the refractory period. This is a period that lasts completely throughout the passing of a stimulus and ends after the cell is at rest. During this time, after a nerve receives one impulse, it is unresponsive to other stimuli. With that being said, let's begin. First in the process is called depolarization. During this time, the activation gates open and sodium ions rush into the cell. The polarity of the membrane inverses. Also, during this phase, the voltage current is established by the influx of sodium ions down the axon. Since there is an excessive amount of sodium ions, the whole membrane becomes positive, and this can be described as an overshoot. The next step of potential includes the inactivation gates, which close for sodium ions to block off further sodium from entering the cell. Activation gates open now for potassium ions with a positive charge. This stage is named repolarization, or restoration of regular electricity. Membrane returns to normal permeability. This is the opening and closing of sodium and potassium gates. Permeability refers to allowing what goes in and out of the cell. During this process, potassium channels begin to close, and the membrane reaches resting potentials of negative 70 millivolts. When the potassium channels finish closing, the charge is all the way down at negative 90 millivolts. This occurrence is called hyperpolarization, or undershoot, due to an efflux or increase of potassium ions from the cell. The resting potential is restored and the action potential is over. The sodium-potassium exchange pump is solely responsible for maintaining the concentration gradients of sodium and potassium. Over time, this process uses 1 ATP for every exchange of 2 potassiums and 3 sodiums.